Hello everybody and welcome to exercise 6. And in this problem, in this video, we're going to be working through just parts A through C of this rather long problem. Okay, and let's start by just reading the first part of the problem to get a feel for what it's asking. Okay, so they're giving us a function little f of x. That's the function that we're given in the graph over here to the right. And we're going to define a new function, capital F, to be the integral from 0 to x of little f of t dt. Okay, so the first observation as we're reading this is that there are two different functions that we're talking about in this problem. There's little f and there's capital F. And it's going to be important to remember that those are different functions as we go through the problem. A key question that we need to answer before we can dive into this is, what is the relationship between these two functions? Okay, well, we can discover that relationship by taking the derivative of capital F. Okay, so doing that would mean taking the derivative of the integral up here that defines capital F and asking ourselves what happens when we take a derivative like that. You might recognize this as the second fundamental theorem of calculus, which essentially says that we get cancellation of the derivative and the integral in this situation. So d dx and the integral from 0 to x are going to cancel out and leave us with the function on the inside. And so what we've discovered is the fact that the derivative of capital F is little f. Okay, so going back over to our picture, that means that this function little f is really the derivative of big F. And that's going to be very useful as we work our way through this problem. All right, so let's see if we can answer part A with that information. So A is asking us for the critical points of capital F. Okay, and you might remember that a critical point is a place where the derivative is 0. Okay, so our answers to this question should be places where the derivative of capital F is 0. Well, up here, we've got a graph of capital F prime, and so we're looking for where that derivative graph is equal to 0. Okay, and I can see a few points where that happens. There's just going to be the places where this graph touches or crosses the x-axis. Those are the points that we want to list. So let's see, what are those? Looks like we've got one at -5, 0, 3, and finally at 5. Those are our answers. Those are the places where capital F prime is equal to 0. Okay. And what about part B then? So this is asking us where capital F is increasing and decreasing. Okay, and again, I remind you that when we answer the increasing part, remember this is asking us about capital F, not little f. Okay, so we have to remember that the graph that we're given up here is not the graph of capital F, it's the graph of its derivative. Okay, so how can we look at the graph of the derivative and tell where the original function is increasing? Okay, well, let's think back a minute here. Okay, a function is increasing where its derivative is greater than 0. So we're going to look at the derivative graph and try to identify the intervals where that graph is positive. And notice that there are a couple. There's a stretch from -5 to 0, where that graph is positive, and another one from 0 to 3. And finally, another one from 5 to 6. So those are 3 intervals where our derivative graph is positive. Those should be our answers. Okay, let's write those down. Okay, and then similarly, capital F is going to be a decreasing function where the derivative graph is negative. Okay, we can see a few intervals like that. So here's a stretch where our derivative graph is below the x-axis, and then here's another one. Okay, and those intervals appear to be between -6 and -5, and then also between 3 and 5. Okay, there's our answer to part B. All right, and then finally, let's look at part C here. Okay, so it's asking us, where does the function capital F of x have a local maximum or a local minimum? Let's start with the local minimum part of that. Okay, and just to help you visualize this a little bit, let's first maybe get rid of some of these markings that we've made on our graph, just so our diagram doesn't get too cluttered here. Okay, a local minimum, if we just draw kind of a rough sketch. Okay, a local minimum is a place where capital F would come to a valley. Okay, and the thing to notice here is how the derivative is behaving on both sides of that local min. Okay, notice that to the left of the local min, we're going down, so the derivative is negative, and to the right of it, our function's going up, so the derivative is positive. So what we're looking for when we look for a local min, okay, let's just write out the words first here. We're looking for a place where the derivative behaves the way that it did up here, where it goes from being negative to positive. So we're looking for a place where our derivative graph goes from below the x-axis to above the x-axis. Do you see any points like that? Okay, I see a couple. There's one here where it goes from below to above, and then there's another one here where it goes from below to above. Okay, and so we've got 2 points, -5 and 5, where our original function, capital F, should have a minimum. Okay, and for a maximum, it would be exactly the other way around. Okay, we're looking for a place where f prime goes from above to below. Okay, do you see any points like that in our picture? Okay, I actually see only one right here at 3. There we're going from above the x-axis to below. Okay, so capital F should have a maximum at that point. Okay, and there's our answer to C.